What's up, lads? This is your boy Jace, and welcome to the Big Brain Busters. So in this video, we are going to be just continuing from part 1 on beta oxidation. So this is part 2. So if you haven't checked out part 1, please make sure you check it out so that we are moving on the same pace. With that being said, let's proceed. So as you can see, if you remember in part 1, we established that the fatty acid chain has been taken into the into the mitochondria, right? That was the preparatory step. So since it has been taken into the mitochondria, in the mitochondria, that's where the big party actually occurs, right? Where we make the actual energy, right? So that energy is what we are going to be basically discussing here. How is that energy doing what? Being formed. Okay. So this is the pathway that we have established. So I'm going to explain each and every step to the fullest. All right, so let's get into it. So now one thing you should know is that here, remember, beta oxidation is a 4-step pathway. It only requires 4 steps, and within those 4 steps it requires a fatty acid long chain being cleaved on the 4th step. So here I'll use palmitic acid or palmitate as my example. So a palmitic acid is simply a 16 carbon chain, all right? And then this 16 carbon chain, when it reaches into the 4th step of beta oxidation, what happens is that is why it is known as beta oxidation, because on the beta carbon of the fatty acid chain, that is where cleavage actually occurs. So in short, acetyl CoA, a molecule known as acetyl CoA, which contains 2 carbons, will be cleaved on the beta carbon. So if you have this guy, it has undergone beta oxidation and it reaches the 4th step, so you find that the beta part, so this is alpha, beta, so on the beta part it will be cleaved, and then again this two shorter carbon chain of this fatty acid will again go back through the cycle, and then when it reaches the 4th step again, this another acetyl CoA will be cleaved off like that, and then goes into the cycle, reaches the 4th step, cleaved there, goes into the cycle, we cleave there again, another cycle, we cleave, another cycle, we cleave, another cycle, we cleave. So you find that we'll be producing 1 2 1 2 1 2 1 2 1 2 1 2 1 2 1 2. So how many acetyl CoAs have we produced? We have produced 1 2 3 4 5 6 7 8. We have produced 8 acetyl CoAs from what? From a 16 carbon chain fatty acid. And then how many cycles has this guy undergone? So it has undergone, so we just count the number of times we have cleaved this molecule. How many times have we cleaved it? We have cleaved it 1 2 3 4 5 6 7. So we have cleaved it 7 times. So in short, this molecule has went through the cycle 7 times. All right. So to be smart enough when doing your calculations, what you can simply do is to find the number of acetyl CoAs that has from this 16 carbon chain, you simply do the number of carbons, which is 16, divide by 2, and then you find what? 8, which is the number of acetyl CoA. And then how about the number of cycles? You just say number of acetyl CoAs minus 1, then you find 7, which is what? Which is the number of cycles. Okay, cool. Then another thing I want you to take note of is that acyl CoA and acetyl CoA are 2 different things. All right, this is a mistake that most of us actually make, but then I'm here to clarify it. Acyl CoA and acetyl CoA, these are 2 different things. Do not mistake them. In that, an acyl CoA, remember we have an acyl CoA, right? So an acyl CoA is simply when we start from C4 to maybe C26. So these are like chains, right? So chains starting from C4 to C26. In short, a fatty acid. When we add a CoA to a fatty acid, we form an acyl CoA. Then when we add a CoA to a 2-carbon chain, which is a 2-carbon chain, we form acetyl CoA. All right, so when we add a CoA to a what is to a fatty acid, we form acyl CoA, and then when we add a CoA to a 2-carbon chain, we form acetyl CoA. These are two different things. All right, cool. So now let's jump into the pathway. So as you can see here, we will complete this pathway by writing whatever is happening. So remember that we're in the mitochondria and we are starting with acyl CoA, right? So this acyl CoA in the first step, the first step is simply dehydrogenation. Okay, so this guy will be dehydrogenated. The acyl CoA, we will remove 2 hydrogens from there. So those 2 hydrogens that will be removed, remember whenever you're removing a hydrogen, you require a dehydrogenase, right? And then you also require another molecule or another compound that will actually accept or receive those hydrogens. So in this case, what we are involving here is simply we have a FAD, okay, a FAD, and then when it receives those 2 hydrogen what's this atoms, we will form FAD H2. Okay, and then since we have formed FAD H2, and then we need to establish the enzyme. The enzyme, we just get the name of the substrate. So the enzyme will be acyl CoA dehydrogenase. All right, nice. Okay, so now that we have formed acyl CoA we have formed so the removal of hydrogens from acyl CoA, 2 hydrogens from acyl CoA, we form trans-ennoyl CoA. So this guy is actually in other books or something or other sources, you'll find it written like that, trans-ennoyl CoA. That's what we have formed from the first step. All right, so that's our product. So our product in the next step, it will be our substrate. So in here, the next thing that we need to do is simply to add a water molecule to this trans-ennoyl CoA. So when we add a water molecule there, so what we're doing is there will be addition of a water molecule. And then what enzymes adds a water molecule? The enzyme that adds a water molecule is known as a hydratase, right? So in short, here our enzyme will be ennoyl. So here, ennoyl CoA hydratase. All right, nice. And then when we add the water molecule to trans-ennoyl CoA, we'll form beta hydroxyacyl CoA. Right, makes sense, right? Okay, so since we have formed beta hydroxyacyl CoA, that will be our substrate in the third step of beta oxidation. So in this third step of beta oxidation, what really happens is that next thing we are removing 1 hydrogen. So we are removing 1 hydrogen from beta hydroxy acyl CoA, and then when we remove that hydrogen, remember that we also need a dehydrogenase to do that work, right? And then we also need something that will actually capture the hydrogen. Okay, so a proton carrier, right? So in this case, what we'll have is a NAD. Okay, so this NAD plus will actually receive the what? Will receive the hydrogen, and then will form NADH. Makes sense, right? And then the enzyme that is involved in this, we still get the name of the what? Of the substrate, the name of this guy, the substrate. So the name of our enzyme is simply beta hydroxy acyl CoA dehydrogenase. Makes sense, right? Cool. So one thing you should know is that the FADH and the NADH that are being produced, they are going into the ETC cycle. Okay, so they are going into the ETC, the electron transport chain, to produce what? To produce energy, where FADH will produce 1.5 ATPs, and then NADH will produce 2.5 ATPs. Okay, so now that we have removed a hydrogen, what will form is beta ketoacyl CoA. So beta ketoacyl CoA, this is the last step of beta oxidation. So in the last step of beta oxidation, remember that we talked about cleaving, right? So beta ketoacyl CoA will be cleaved. So what will cleave off from beta ketoacyl CoA is simply a 2 carbon molecule known as acetyl CoA. And then since this 2-carbon molecule is coming out, is being cleaved off with an acetyl CoA. Remember acetyl CoA again, to go into the what? Into the, so the acetyl CoA that is being cleaved off is going into the Krebs cycle for production of energy. All right, so in the Krebs cycle there, what we will produce is simply three what? Will produce 3 NADH molecules, 1 FADH, and 1 GTP, which is equivalent to 1 ATP. That is where the acetyl CoA will go. And then now remember that we have removed a CoA, so meaning that we need something that will add a CoA. So we will add a CoA here. All right. And then when we add a CoA here, what will form is another acyl CoA, back to square one. All right, but then this time this acyl CoA we have formed, it is 2 carbons shorter. That's a very important thing. So if we had palmitic acid, meaning that, which is 16 carbons right now, this what's this, our next acyl CoA, it will be 14 carbons. All right, and then the thing is, it will now undergo the same step. It will go back and then restart the what? The cycle, and then the cycle continues. So we're going now to talk about, you know, how to calculate the energies from whatever we've talked about here. So to calculate that, let's jump into it. Oh, and sorry, we forgot to mention the enzyme that was being used to convert beta ketoacyl CoA to acyl CoA, which is 2 carbons shorter. So the enzyme is simply beta ketoacyl CoA thiolase. All right, so like we said, we want to establish the number of ATPs in beta oxidation using the example palmitic acid, right? So right now, since palmitic acid is a 16 carbon chain, right? So this guy, what will happen is that what we're simply doing here, we are taking into consideration also in our calculations. Remember, I told you to say in video 1 that we need to consider those 2 ATPs that were actually used, right? Because we use them to find our net ATP. So those 2 ATPs that we used to produce acyl CoA, right? Those 2 ATPs, we need to consider them when calculating our total. All right, so in our calculations, let's determine step 1. So step 1, let's calculate the number of acetyl CoA. So number of acetyl CoA, all right, we simply said here we had just counted, right? But then here, simpler way, when doing your calculations, you simply say number of carbons, which is what? Which is 16, since we're using a 16 carbon fatty acid. Then we divide by 2, and then when we do that, this will give us 8 acetyl CoA. Okay, and then after we do that, next thing we determine simply, so the next step should be, like, we determine the what? We determine the number of cycles, right? So to determine the number of cycles, we said that we can just simply say the number of acetyl CoA, which is 8, then we just subtract by 1, because here to find the number of cycles we had just counted the number of times we had cleaved this compound. But then easier way, we just say number of acetyl CoA minus 1, which is 7 cycles. So what's the significance of finding the number of cycles? So the significance of finding the number of cycles, remember that in our entire pathway, in one cycle we were producing 1 FADH and 1 NADH, right? So these guys also will be used to produce energy in the electron transport chain. So if in one cycle we are producing 1 NADH and 1 FADH, how about in 7 cycles? So step 3, we find number of NADH. So 1, so meaning that we'll have 7, right? 7 FAD H2 and 7 NAD H. So if we have 7 FAD H2 and 7 NAD H2, we can convert them into into ATPs, right? So to convert in the electron transport chain, what simply happens is 1 FAD H gives off 1.5 ATP. So we can just say 7 times 1.5. So we'll say 7 by 1.5, which will give us 10.5. So it will give us 10.5 ATP. 0.5 ATP, and then here we multiply by 2.5, since 1 NAD H gives us 2.5. How about 7? So 7 by 2.5, 7 by 2.5, which will give us, should be 17.5. Okay, so 17.5 ATP. Then let's calculate the total out of this. So the total out of this, so we add what? We add the 10.5. So when we add the 10.5, it gives us 28 ATPs. So 28 ATPs that have been produced from here. All right, cool. So let's take note of that. And then step 4. So step 4, remember that the acetyl CoA that was being produced, will go into the Krebs cycle. And then in the Krebs cycle, so here we are calculating number of ATPs produced in Krebs cycle. Okay, so the number of ATPs produced in the Krebs cycle. So whenever the acetyl CoA goes through the Krebs cycle, if you don't know about the Krebs cycle, please research more about the Krebs cycle. So in the Krebs cycle, one thing you should know is that we always produce three NAD H, one FAD H, one FAD H2, and one GTP, which is equivalent to one ATP. All right, so here our goal is simply to convert these other ones, because this one is already converted. So 3 NAD H, we multiply by what? By 2.5 ATPs when it goes into the ETC, and then 3 by 2.5, which should give us 7.5, I think 7.5 ATP. All right, and then what's next? We convert the number of FAD, so multiply by 1.5 ATP, which should give us another 1.5 ATP, and then plus 1 ATP there, 1 ATP. So this plus that should be 9 ATPs plus 1, 10. So you should know that whenever one acetyl CoA goes through the Krebs cycle, it always gives us 10 ATPs. 10 ATPs. But then, since remember how many acetyl CoA had we determined? We determined 8 acetyl CoAs. So meaning that we will find 10 multiplied by what? By 8, which should give us how much? 80 ATPs. All right, so now step 5, let's determine step 5. So step 5, let's find our gross ATP. So our gross ATP, we are simply adding the 28 plus the 80. 28 ATP plus the 80 ATP, which should give us 108 ATP. All right, so this is the total ATP amount of ATP that has been produced throughout the entire beta oxidation. So now our last step is simply to calculate the net ATP. So the net ATP, that's where now video 1 comes in. So if you haven't watched video 1, I'm sorry, you need to go back, but don't worry. So in the preparatory stage, when producing acyl CoA, we used 2 high energy molecules. So those 2 high energy molecules, we need to remove them. We need to subtract that. So we need to say 108 ATP subtract by 2 ATP, which will give us 106 ATP. All right. So this is our net ATP that will be produced from 1 mole of palmitic acid. Wow, we've had a long time. So let's now just do the last thing, which what things actually regulate beta oxidation. So regulation of beta oxidation. So some things that regulate beta oxidation are the first thing is when you have high concentration of free fatty acids. So when you have a lot of free fatty acids, they can actually regulate beta oxidation. All right, because you don't need to break down a lot of fatty acids to produce energy when you have a lot. So high free fatty acids, like also Another thing that regulates is simply um, when you're in a fed state, all right? Fed state. Another thing, hormone sensitive lipase. So this hormone sensitive lipase is also sensitive to, it is also sensitive to what? To high concentration of free fatty acid, in that things like hormones such as glucagon and insulin, we know that glucagon lowers the amount of ATPs being produced, and then insulin, yeah, lowers, then glucagon versus increases, right? So whenever you have a lot of ATPs, insulin will come to lower the beta oxidation, and then whenever you have low ATPs, we need glucagon to come and higher the amount of ATPs. Well, this has been a long video, guys, so thank you very much for watching, and please do not forget to subscribe to our video or channel, and don't forget to also like, share, and comment on the future videos that you would like us to actually you know maybe explain and stuff and include on our channel. Otherwise, enjoy your day. Shalom, shalom.